Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
We have looked at some of the causes of or sources of electrical hazards or sources of hazards in electrical devices, and you mentioned fire outbreak. Okay, I thought someone will talk about water. That's why you are advised not to bring water close to electrical socket, is it not? You know that water is a conductor, even though it doesn't conduct as much as metals. Water conducts. It's a poor conductor, just like the human body. But it conducts. Do you agree with me? In fact, if you remember your chemistry, there's what we call polar covalent bond. H2O or water forms a polar covalent bond, just like hydrogen chloride. Polar covalent compounds can conduct electricity. Polar covalent compounds can conduct electricity. So water can conduct, electricity, though not as much as, metals are good conductors, but it can conduct. So you should avoid water touching electrical devices or electrical components like sockets, because the water might breach the circuit and result to a serious damage to your appliances. Now, one of the ways we try to protect our devices from being damaged is the use of the fuse. Do you know fuse? Let's talk about the fuse. What's a fuse? Do you know the symbol of a fuse? Do you? Are you sure?
I don't.
Okay, this is the symbol of a fuse. That means a fuse is a resistant material. Because if I didn't have this central line, what would it have been? Let me even clean it. If I had cleaned off the central line, and had only this would have been called what? What kind of resistor? A fixed or standard resistor. But if you have a line passing through like this, it is called what? A fuse. By the way, what would you call this, just for emphasis? What's this called? You know what this one is called? This is a heater, electrical heater. Well, of course, this one is a fuse. They are all resistant materials. Give me other resistant materials. Thermistor is a resistant material. Light dependent resistor. LED, variable resistors. They are all resistant materials. Okay, now, how does a fuse work? A fuse, not a transformer. It explodes. So you have an idea, and I'm happy that you have an idea. Now, a fuse has a resistant wire. So it's a resistant material. So let me introduce the fuse here. We usually connect the fuse to the positive side of the battery and also to the live. I'm going to talk about all that as we continue. This is the fuse. Which side is it connected? To the positive side. Okay, now you have your components. I will carry out the connection before I talk about the rest. Or what can I use? Okay, let me use this. This is too big, but let's just manage it. Now, when, like you said, if this lamp, an expensive lamp, is rated 5 volt, 4 amp, or 10 amp, or whatever, and the battery is supplying the 5 volts, now for any reason an excess current flows through and wants to, or an excess current wants to flow through. What I mean by an excess current? A current bigger than the rating of this appliance. The rating of the appliance is 5 volt, 4 amp, right? Or maybe it can be given in terms of power, 5 volt and the power rating. With the power rating, you can easily calculate the current. Can I just put it in terms of power? 20 watts, 5 volt, 20 watts. So what's the current that will flow through? You know P is equal to IV, is it not?
Yes.
All these formulas, you should remember them. P is equal to IV, so the current will be what? I is equal to P over V, isn't it? P over V, which is 20 over 5, and that's 4 amps. So this is usually rated in terms of its power, 20 watts, and so on. And of course the voltage that it will require to work properly. So 4 amps is what this lamp will take to work at its optimum rate. But if for any reason a current higher than 4 amps flows through, you know it can damage this lamp. And to protect this lamp from that, you connect a fuse. Now if that current wants to flow, the current will melt the fuse and the fuse cuts off. If the fuse cuts off like this, what I'm saying is, assuming for any, if a fault develops along the circuit and a current of say 5 amps and above wants to flow through, the fuse will melt and cut. The fuse actually has a wire that runs through it, like you can see. So when the wire melts and cuts off the current flow, it protects this your device from that high current. Is that understood? I've said all of that to say that a fuse is a protective device made up of a resistant material. So let me write it down. It's a protective device. Protective. That cuts off excess currents, thereby protecting your component from damage. It's a protective device that cuts off excess current, and of course it cuts and disconnects the circuit, and protects your device from damage. How does it work? When that current is too high, when the current is too high, this wire will melt. We heat up and melt, and when it melts, it cuts off. Once it cuts off, it's like you are opening the switch. You know what I mean by opens the switch? The switch is open, like I showed earlier. Can currents flow at this point? So what has been protected? The lamp has been protected. All we need to do is replace this fuse. Once you replace the fuse, the current flows. And before you even replace the fuse, you need to check for whatever is the reason for that excess current that was flowing in the first place. what we call current surge. Pardon? Yes, please.
You use, let's say, copper to join the batteries to.
Yes, of course. That's what we normally do. You know, fuses are cheap. It's better to blow up a fuse than to damage your component. Fuses are so cheap that you can replace them as many times as possible. So the wise thing to do is have your fuse blow and then replace it, than allow that excess current to flow and then damage your expensive phones, devices, gadgets, and what have you. So, like you said, you can just use a copper wire to reconnect from this end to this end, and the fuse picks up. But whatever you're going to use should have a proper rating that will not allow excess current to flow. And so fuses are rated. If a fuse is rated at 5 amps, for instance, it means it shouldn't allow a current more than 5 amps to pass through. If you look at the fuse, you see a rating of the fuse on the surface body of the fuse. If you have a fuse rated 5 amps, the maximum current you can allow will be anything above 5 amps. It will do what? It will melt or cut. Or the term we use is blow. So what I say a fuse is? And so protects our devices from being damaged, right? And protects devices from damage or being damaged by those excess current. That current surge. All right. I was trying to tell you that the fuse heats up because of the current. If you know, electrical energy W is equal to IVT, is it not? Which of course is equal to I squared RT. Do you know? Do you still remember these formulas? We proved them earlier. What's the problem? Can you see it clearly? Electrical energy W is equal to IVT. It's not difficult to get because power is equal to IV. What's the relationship between power and energy? Energy is power times time, is it not? So, what is power again? IV. So, if energy is power times time, energy will be what? IV times T, which is or power times time, or IVT. And if you remember your Ohm's law, voltage itself is IR. V is equal to what? We've done all this. You can check back where we did them. V is what now? If you substitute V in this place, you have I squared R, because I times IR before T will give you I times IRT, or I squared R. Now what I'm trying to say is current has a geometrical effect on energy. Listen very attentively and make sure you get this. In this formula, you have I squared RT. What does that mean? Anything that happens to current will have a geometrical effect. You know what I mean by geometrical effect? Like the effect will be so much, because you still have to raise the current to power 2. I can give a simple example. If for a particular situation, for a case 1, where R is 5 ohms and the current flows for, let's just use simple unit, 2 seconds, and the value of that current, this is case 1. Can I just say case? What can I say so that you don't mix it up? Okay, the current is, what can we give for current reading? Current reading 4 amps. Let's calculate the power, the work done. Sorry, the work. What's the work? Or the energy transferred? I squared out, is it not? Which is what?
25 50.
4 times 4. 4 squared times R, 5 times 2. What does it give? 16 times 5. Please use your calculator quickly.
170.
In fact, 160 now.
165 times 210, 16 times 10.
160 joules, is it not? 160 what? Okay, let's double the current. That is case 1. Let me write it properly. Case 1. I want you to double the current. Let's double the current. Double the current. Case 2. Current is doubled. All other things, factors remain the same. Only current is doubled. What is R again? Let's write them the way they were. R is 5 ohms. T is still 2 seconds. Now current is now doubled. Current is now what? 8 amps, right? Let's see the energy. Work done. Work done is equal to I squared RT. Are you listening? That will give us 8 squared times 5 times 2. And what will it give? 640 joules. Can you see the change? Did you notice the change? From 160 to 640 joules. What did you just do? We only doubled the current. We just made the current from 4 to 8. Sorry, from 4 amps to 8 amps. From 4 amps to 8 amps. And the energy has changed from 160 joules to 640 joules. That's a lot. Did you get that? So it means the effect of current is so much on the energy. That's why, like I told you in Ohm's law experiment, can you mention one of the precautions you take in Ohm's law experiment? In investigating Ohm's law, one of the precautions.
Change. Switch off your.
Switch off in between readings. Switch off what? What are you trying to reduce in this formula when you are switching off in between readings? In this formula, because it's all about energy. What are you trying to reduce? Is the time. The time that the current flows. You know, when you switch off, you are reducing the time the current flows. Do you understand? There are factors that affect the energy. What are the factors again? Current, resistance, and time. So when you switch off in between reading, you are reducing the time, so less energy, which means less heating effect. Less what? Heating effect. All of that is to reduce heating effect, or to prevent it, or minimize heating effect. What else do you do? I said switch off in between reading, put it in a water bath so that it will cool off by itself. There's one particular one I say you must always remember. Use a low voltage power supply so that the smaller current will flow. Did you understand what I said? Because current has a very major effect on the energy. As you saw, a current of 4 amps, we got an energy of 160 joules. But when we just doubled the current from 4 to 8, see how the energy jumped from 160 joules to 640 joules. That's a lot of change. So you need to reduce the current as much as possible. Now what I'm saying is, if a high current is flowing, that means a lot of energy. A lot of what? A lot of electrical energy that can convert to heat energy, that can convert to what? Which is going to melt the wire that runs through the fuse. It is that heat energy that causes the wire to melt. And once the wire melts, it cuts off. And as it cuts off, the current doesn't flow again, so it protects our device from damage. That's the principle of operation of a fuse. Now, instead of a fuse like that, we can use what we call circuit breakers. Have you heard of that? Now, circuit breakers work on the principle of electromagnet, which we're going to talk about later. I said circuit breakers can perform this same function. Okay? Circuit breakers can perform this function. Now, the advantage of a circuit breaker is you can just reset it. When it happens, you reset it instead of changing the fuse completely. You know, this one we have to change the fuse, completely. But the circuit breaker, they said a lever you may need to pull or a button you may need to press, because when it cuts off, when it trips, it's just a disconnection that by bringing down the lever or taking it up or pressing it down, it reconnects. Now, if that fault is not solved or sorted out, if the fault is not sorted out, when you connect the circuit breaker, it can still trip again. Just like if you didn't solve the problem initially, and then you connected the fuse again, it will still cut. So the first thing is to solve whatever caused the high current surge before you replace the fuse. Solve the problem that caused the high current surge before you replace the fuse or you reconnect the circuit breaker.
So why do people still choose to use fuse?
Instead of circuit breakers. That circuit breakers are costly. You can't and you can't be using circuit breakers for every component. But with a small fuse, in fact, even your adapters and what you have fuses. If you get an adapter, those plugs, if you check underneath, you really see the fuse and the rating. But circuit breakers are bulkier. Okay, that's about one at electrical hazard and prevention. I've told you that when you plug in your components and you allow water to come in contact with the plugs, it can pose a hazard, isn't it? Because water is a conductor, it can breach the circuit and result to serious damage. I just need to tell you something about electrical connection. Look at this. By the way, this particular current that is flowing is a direct current, DC. For a direct current, we talk about positive and negative. But for an alternating current that you get immense supply, we don't talk about positive and negative, we talk about live and neutral. And sometimes you have an earth wire. The live is like the positive. The neutral is like the negative. Then the earth wire is for protection. Depending on the color code for that country, live is usually red or sometimes brown. Neutral can be blue or another color. Earth, green. But it depends on the color code that is used for that particular country. But usually live is red, neutral blue, earth brown, earth green or yellow. They use yellow too for earth. So, and sit up. Sit properly. Sit up. I said this is for alternating current. Live for alternating current is equivalent to what?
Positive.
Live for alternating current is equivalent to what?
Positive.
Positive in direct current. Neutral for alternating current is equivalent to negative in direct current. The earth wire is for protection. I just want to tell you how the earth wire works. I can illustrate it here, and that will be very quickly. There are certain devices that will not require an earth wire. Stay alert. I need to conclude this very quickly. there are certain devices that will not need an earth wire. What we call double insulated devices. They don't need an earth wire. By the way, have you opened, you've seen certain plugs that have 3 legs. Let me see that plug there. Of course, when you plug it in, you notice that it has 3 legs. That 3 legs, the first 2, usually side by side, are the lives and the neutral. The other one is the earth. Pardon? This one does not require it doesn't require the use of earth. That is just to help to open up that space so that you can plug it. Some devices do not require earthing wire because it's double insulated. In fact, let me tell you, double insulation means the device itself is covered with an insulator, like this electric fan. The whole thing is covered with an insulator. There's no danger of electrocution, and so you don't need an earth wire. If the device, you can be sure that it's completely covered with an insulator, there's no possible danger of electrocution, so you don't need an earth wire. Because an earth wire is just for protection. This is how it works. I want to explain it. So you listen very attentively. I will make it very fast. This is the live connected to the main, which is an alternating current. I want to show you something very quickly. What I think I should rather draw is the component. Let me draw the component here. Please stay alert. Any problem? Any problem? Okay. Pay attention. Pay attention. I want to explain something. Just for the purpose of illustration, I want to explain something. Just for the purpose of illustration, I want to explain this. Watch this. Okay, how do I run this? Okay. All right, so this is what we have. We have main electricity. When I say main electricity, I'm talking about alternating current electricity supply. You know, that's the one supplied by power holding companies, not direct current. This symbol, do you know what it is? What is this symbol? I'm coming, just a moment. What is this symbol? This means alternating current. It means what? What did I say this is? This is a fuse, right? I told you that the red wire represents what? Oh, it's not showing red at your end. Okay, that's the red. This one I'm tracing is the red. That's the live, right? Why the blue wire represents the neutral. This is mains. It's alternating current now. So the red is live, the blue is neutral. Now, if this component I'm circling, is completely insulated, what we call double insulation, it does not require an earth wire. But if there's any danger of a part of it being exposed, a metallic part of it, a conducting part of it that can be exposed for anything to the human body, you need an earth wire. This is how and why we need an earth wire. This is how, first of all, this is how an earth wire works, and this is why we need it. First of all, this is how it works. If this live wire accidentally makes contact with the body of this appliance, this thing you're seeing here is an appliance. It could be your washing machine, it could be your electric fan, it could be your pressing iron, it could be anything, usually anything that uses high current. Did you get me? Think of this as maybe a washing machine or electric iron. Let me just use a simpler one, electric iron. So if it's an electric iron, it should be a heater now, isn't it? So maybe I should use a symbol of a heater. I told you this thing represents what? This thing represents what? A heater. So if this is an electric iron, I can use this because it produces a heating effect. Now, and it uses sufficient current. Because we want heat, we really need the heat. We need the current to be high, is it not? What did I tell you current has? What effect did I tell you current has on the energy? A geometrical effect. Once current increases, it causes the energy to increase rapidly. So we need higher current. Now, this live wire, if it accidentally touches the body of this electric iron by accident, maybe there's a fault that has developed. I think I should use a different color. Let me use a different color to represent that. I'm going to use this yellow line. This yellow line is a strand of wire. Okay, maybe I should put it here. Let me put it here. There's a strand of wire that accidentally touches the body of this electric iron. This strand of wire is coming from the live, and it accidentally touches the body of this electric iron. Did you get that? Now you are using the electric iron and you hold it. What's the implication? Yes, now the human body is a conductor, and you accidentally touch the electric iron. It means you become connected to the live. Because the body of the electric iron is now connected to the live because of this strand of wire from the live that is touching the body. Yeah, that's why I'm saying if the whole iron itself is fully an insulator, there wouldn't be any problem. But can you make the entire iron to be an insulator? Which surface will you use to iron your cloth? Are you getting what I'm saying? Can you make the entire body of the iron to be an insulator? It's not because we don't have any surface to iron your cloth. The surface should be at least a solid iron, metal. Is it not? Are you getting what I'm saying? There are certain devices that it will be almost impossible to make the whole thing an insulator. I just gave you an instance, an electric iron. So now, if by accident a strand of wire from the live makes contact with the body of this iron, this body becomes live. The body becomes what? Live. And so if an operator, the user, touches it, the user gets electrocuted. So to prevent that from happening, what do? Now you watch it. This is what we do. We connect another wire which we call earth. This is a symbol of earthing. I've given you this tip before. I don't know if you remember. Do you remember that? What does this symbol represent? It's earthing. Earthing or earthing wire, which is also grounding. That's an earthing wire. Now this is what the earthing wire does. Watch me. Are you listening? If by accident a strand of wire from this live red wire makes contact with the body of the iron, current will now flow from the live to the body of the iron and then to the earthen wire. Did you see that? To the earth. Let me trace the process again. Are you listening to me? If a strand of wire from the live accidentally makes contact with the body of the iron, current will flow from the live to the strand, to the body of the iron, and to the earth wire, and that will cause a large current to flow quickly. That large current that is going to flow quickly will blow the fuse. We do what? Blow the fuse. So once that happens, the fuse cuts. Even before the user we mistakenly touch the iron, the circuit is already broken. Will current flow at this point now, when the circuit is broken? Is the current still flowing? Why? Why is the current not flowing? The fuse has been broken. So a user who wants to use the iron cannot be electrocuted. But will the iron work? The iron is not going to work. What do you need to do? If you replace the fuse, listen very attentively, if you replace the fuse, current will flow through the live wire and enter through the strand that makes contact with the body of the iron, and from the body of the iron through the earth wire and then to the ground. The fuse will blow again.
So why is the fuse blowing? Current too much.
Yes, why is the fuse blowing? Because this current that is flowing through the earth is pulling so much current. Pulling what? More than the required specification of the electric iron. So the amount of current that is being pulled or drawn is higher than the rating for the iron. Assuming normally when the iron is working properly, it uses 10 amps. Listen, when the iron is working, you asked a very good question. When the iron is working properly, it uses 10 amps. Working properly, because the current will have to flow the normal way through the iron. So only 10 amps. It flows the normal route through the iron, so it uses 10 amps. Are you listening to me? But when the current did not flow through the normal route, it just entered through the body of the iron because of what we call short circuiting.
Does it get more current?
Now, it's not that listen to me. It's going through the body of the iron bypassing this route. Please stay where you are. Bypassing the route. Because it is bypassing the route, it is going through lesser resistance, smaller resistance. Did you hear me? If current flows through a smaller resistance, what happens?
Then
More current. Because it is not going through the route where it has a large resistance. Yes, when it is flowing through a smaller resistance, because there's not much resistance in the path, the large current will be drawn. That large current drawn will be higher than the rating of the fuse. Remember, the fuse is supposed to be rated 10 amps. Hold on before you ask your question. The fuse is rated 10 amps because the electric iron should not have more than 10 amps when current is flowing through the normal routes where there's enough resistance. But now if there's a fault, an electrical fault, and there's a strand of wire from the live that makes contact with the body, such that this current does not go through its normal route, but it now enters the body of the iron, and from the body of the iron to the earth, it has been short-circuited. So it's not flowing through the normal route where you have a lot of resistance. That means there's a lower resistance. There's what? Which means what? More current. So a larger current, like 15 amps, we want to flow. We want to do what? As it just flows through the fuse, what happens to the fuse? The fuse blows. In other words, it melts and cuts. And once it cuts off the current, no current can flow now. The user will not be electrocuted, but the electric iron will not work. And if it won't work, if you connect the fuse again, it will blow again. So what do you need to do first? You must rectify the fault here. How do we rectify the fault?
By repairing.
Repairing this, making sure that that strand of wire is no longer making contact with the body of the iron. Let me complete it. This is the way it should be so that it will work properly. If it is now the proper way, such that the strand of wire or the live is no longer making contact with the body of the electric iron. Now you can ask your question.
Okay, well, I don't understand the flow.
Yes, the flow is the normal flow. This is the normal way it should flow.
Yes, but like when
See, hold on. First of all, let me say, this is the normal way it should flow. Watch me as I trace it. From the live, through the electrical wire, and through the electric iron, then to the neutral and back. Is it not? From the live, through the electric iron, or through the resistant materials, then to the neutral and back, where it uses the normal value of current, 10 amps. But if there was a fault, if there was what? It is short, the route is short-circuited. You know, when we say something is short-circuited, you have bypassed that route. Once you bypass instead of going through the normal route, through the resistant material, it will enter to the body of the electric iron. And when it enters to the body of the electric iron, it flows through the body of the electric iron to the earth.
Yeah, well, so how if it goes to the earth?
I said this, when it is going to the earth, yes, some will still flow. But I'm saying that because it is going through what we call a path of least resistance. A path of what? A path of smaller resistance. A path where the resistance is...
Well, so the ones that went through
Just hear me out. Just because it is going through the route where the resistance is smaller. Where the resistance is what? That's why the current becomes bigger and so it blows the fuse. That's all that we require here.
well, it goes through the earth things, but how does it now return back to the normal?
It's not about returning to the normal. It's not, see, once you know the earth is a reservoir. It's not even about going back to the power source.
Go back to the
Yes, it can go to the earth. Yes, it can go to the earth.
Because it's pulling it up.
You remember when we were doing, don't forget when we were doing electric fields, when we were doing static electricity. When we were doing static electricity, I told you that you can connect your hand to the body of the charged object and electrons can flow through your hand to the earth. All we need is for electrons to flow. It doesn't have to come back here. All we need is for it to flow.
So is it that they flow the electron now? The flow that went through on the resistivity is not that much again?
Yes, I said it. I said that already. That the current, the charge that is flowing through the body of the iron to the earth wire passed through a smaller resistance. Passed through what? And because of that smaller resistance, what happened? More current. And more current blows the fuse. So it cuts off that current and protects your device from getting damaged.
So the resistor need an electron to be able to function the way they're supposed to function.
What did you say?
The resistors, they need electrons to be able to function the way they're
Resistors are resistant materials. They just oppose the flow of current. So they will not allow too much current to flow. What's a resistor? A resistant material. What's resistance? Opposition to the flow of current. Resistors will at least reduce the amount of current that is flowing. But if it didn't pass through the resistors, it won't have so much opposition. That means so much current will flow. Alright, so
flowing out of the flow.
just a moment, please. Yeah, just. You know, short circuiting always occurs when current finds a path of least resistance. For instance, if you have this circuit, let me zoom in a bit. Whenever current finds a path of least resistance, it flows through that path and it will boycott other parts. Like if you have this, I have this circuit, and let me draw with a simple circuit to illustrate that. If this is a resistor, which is one of the paths the current can flow, and we have this, and then there's another path like this. In fact, let me even represent this with a bulb, a lamp, which of course offers a form of resistance. This is a lamp on this path. A light bulb or a lamp on this path. Now, if you have a switch here, let's represent here, let's add a switch here. In fact, two switches, switch here and switch here. Let me call this one switch 1 and this one switch 2. If we close switch 1 and open switch 2, that's if this switch 1 is closed, current can actually flow through this path 1 and the lamp will come on. This lamp can come on if only switch 1 is closed, that is on. If only switch 1 is on, current can flow through here and the lamp will come on. But if we close both switch 1 and switch 2 like this, we close this and we also close this, current will bypass the lamp and follow this path where there's not much resistance. It will follow this path. It's going to follow this outer loop. So it will go through here. Once you get to this junction, it will not flow through this route. It will flow through this route where there's not much resistance. So this lamp has been short-circuited. In other words, it's been bypassed. No current will flow through it. If at all, it may be a very little current that can flow through it. So we say that the lamp has been short-circuited because the current will now flow through this outer loop. And why is it flowing through this outer loop? Because there is not much resistance in its way. So we say that current flows through the path of least resistance. And that is what short-circuiting is about. So the current that gets into this junction will not want to go through this route. It will flow through the outer loop where there's not much resistance, nothing in its way, so it just follows that route and come back. So the lamp has been bypassed, so the lamp will not come on. So what I'm saying is, even when these two switches are on, closed, that is on, you turn this on and you also turn this on, that's the two switches are on, the lamp will not come on because current will flow through the outermost loop and bypass the route where you have the lamp. So we say that the lamp has been short-circuited. So when you close switches 1 and 2, the lamp will not come on. The only way the lamp will come on is to open switch 2. If we open switch 2, the current of course has no other choice than to only follow this route 1, the path where you have the lamp. And once switch 2 is also closed like this, like you close switch 2 together with switch 1, current will bypass the route where you have the lamp. We say the lamp has been short-circuited. That's how short-circuiting works. Okay. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.